Hey y'all, welcome to another video. Today I'm talking about the concept of a Thévenin equivalent circuit. And yeah, broken record here, this is super important. I guess I should just stop saying that, because to be honest, this is EE 101 I'm trying to cover. So really every episode of this is super important, it's super fundamental. Every engineer would do good to refresh themselves on these concepts regularly. So this is the stuff that real engineers use every day. With that being said, let me get on with it. What do I mean by a Thévenin equivalent? I've sort of touched on this topic before, like black boxing, and it's sort of similar to the idea of creating parallel and series equivalents. Basically, the whole point is to make circuits easier to deal with by abstracting away all the complicated messiness that we don't necessarily care about. So, for example, everything in this squiggly box is a big, messy, arbitrarily large and complicated circuit composed of, let's say, resistances and sources. They could be dependent or independent, but you have to be careful here. If there are any dependent sources controlled by variables, you need to make sure that everything is contained within this box. Also, this only really makes sense to talk about if the circuit that you're analyzing has two terminals, or one spot at which you're looking for a resistance, a voltage, and a current. There can be other terminals, other taps, other spots where the circuit connects to things at any level of hierarchy, but if you want to make an equivalent model for some level of the circuit, you have to make sure that the part that you're looking at, you're only considering looking between 2 points, and then everything else can be absorbed into a box like this. And then what you do is you pretend that that entire circuit is just a single independent voltage source and a single resistor. You take this circuit, no matter what's in there, if you look across these two terminals, what you'll see is some voltage, some resistance looking in, and if I were to draw a wire across the terminals, some current would flow. So you take those three characteristics, the fact that there's a voltage, a resistance, to a source. If I applied a source here, there'd be some resistance looking in, and also the fact that if these nodes were connected, some current would flow. It turns out that that can completely describe this circuit in terms of any interaction that we would have with it from this spot looking in. Because if I'm just going to connect this circuit to something, or connect something to this circuit at this point, ultimately that voltage, current, and resistance fully describe any interaction that could take place. So we may as well model all of this nonsense as something this simple. Okay, the first thing is determining this source voltage, VT, and the T stands for Thévenin. A lot of times you'll see this VTH. You might see RT, RTH. It's all the same thing. It's the Thévenin voltage, Thévenin resistance, VT, RT. This voltage that's generated by this source must also appear across these open terminals, because this resistor is just hanging off here. There's no closed circuit really, so no current can flow, and therefore the voltage VT also appears across these nodes. For that reason, the Thévenin voltage in a Thévenin equivalent circuit is also called the open circuit voltage, because it's the voltage you see across the nodes when they're open like this, denoted VOC for V open circuit. And it's the same thing as V Thévenin. So V open circuit is literally just looking at your circuit, just measuring it, looking at the voltage between 2 points. So then the question is, what's the Thévenin resistance? Another way to think about that is, what's the resistance looking in to this port, or this input or output, or whatever this is? One thing you could do is look at the open circuit voltage combined with the short circuit current. So if I put a wire here and then measure the current flowing, a lot of times that's called ISC, I short circuit, that will give me the last piece of information that I need, because RT will say equals VOC divided by ISC. This time you're actually going to change your circuit. You're going to connect a wire across those two nodes, and then you're going to recalculate with some KVL, KCL, some sort of circuit analysis, what the current would be flowing through that short circuit. Then you take those two numbers and find this ratio using Ohm's law, and that gives you your Thévenin resistance RT. And then that completes your model. You have a Thévenin equivalent circuit. Let's just walk through this and talk about how you generate this model. So let's say you have an original circuit that looks like this. We have a 15 volt independent voltage source with a 100 ohm resistance and a 50 ohm resistance like this. And just for clarity, I'm saying like this in the dashed lines is our resistances and sources. This is our original circuit. And this is the big messy monster, let's say, in here that we don't want to deal with, right? And then these little nodes sticking out, like those are there because I choose to put them there. You know, those are spots that I choose to analyze. Like this really might be the entire circuit like that. It's just two resistors and a voltage source, and it's, you know, it's doing something. And then I'm saying, well, I want to look at it from this perspective. And then I'm going to use this in some way. It might be because I'm going to attach something here, right? So then I want to say, like, well, let's just model this as a single source and a single resistor. How can we get there? So the first thing, like I talked about, is let's measure the open circuit voltage. And there it is. I've got two nodes here. They're open. So what's the voltage across these nodes? So what you would do, I think pretty clearly, is use KVL, or voltage division analysis, and just find really how much voltage drops across these resistors. And once you have the voltage across the 50 ohm resistor, you have the open circuit voltage. Given the ratio of these resistances, 2/3 of the voltage drops across the 100 ohms and 1/3 drops across the 50 ohms. So we know that we've got 5 volts here across these nodes. So that equals V Thévenin equals VOC. Okay, great. We're already halfway there. Look at us go. So now, how do we get the R Thévenin? Well, like I said, we're going to have to calculate the short circuit current. Okay, so I've just redrawn the circuit, but with the short applied across the nodes. So we've shorted the terminals that we want to look between. And then I even drew one more little circuit just so you see the equivalence and don't get distracted here. So because I've shorted these nodes, what we have is a short circuit or zero resistance in parallel with this 50 ohms. So it's equivalent to just saying the short or zero still. This 50 ohms plays no role on the circuit at all because there's a short here. So you can just draw it with the 50 ohms removed. And this boils down to just an independent voltage source and a single resistor. So at this point, this should be totally trivial to you. Given that you have a voltage and a resistor, it's just Ohm's law for I short circuit, which in this case equals 15 divided by 100, or 0.15 amps. Okay, great. And given that we know V Thévenin, or VOC, V open circuit, and we know I short circuit, we have our Thévenin because it's RT equals VOC over ISC. We'll do us a little bit of algebra, and we have that our Thévenin equals 33.3, you know, repeating. Ohms. And if I want to, you know, draw out that model just for completeness, and now interacting with these nodes, with this terminal here, the stuff in this box completely mimics the stuff in this box. So this 15 volts, 100 ohms, 50 ohms, it could be 5 volts and a 33 ohm, and you would not know the difference as long as you just interact with these terminals on the outside. It gives you equivalent behavior in terms of resistance, voltage, and current. And I know that this is only marginally simpler, but you would still arrive at something this simple, even if this circuit was arbitrarily complicated. So this is very valuable, very powerful, and you absolutely must learn how to do this. So again, thanks for watching. I hope this was helpful, you guys. Let me know if you have any questions. And have a great day.